Hey Team Bio, welcome to your next screencast on the Big Four Part 3, enzymes. We're going to be talking today about the induced fit model and inhibitors, things that block the induced fit model from taking place. Okay, so we talked yesterday in class, or 2 days ago in class, about this induced fit model where we have a substrate right here. This is going to be our reactant. In our chemical reaction that our enzyme is going to catalyze. And the way that the induced fit model works is that the substrate diffuses into the active site of the enzyme. So remember, there's random molecular motion. If things are at a temperature that is above absolute zero, the substrate is just going to be bopping around in solution. If it happens to diffuse into the active site of the enzyme, then it's going to bind. That is going to cause a conformational change in the enzyme. The enzyme is going to change its shape, and in that conformational change, the substrate is going to be positioned in a certain way such that it lowers the energy of activation to make the reaction happen, and then it's going to be converted into our product, which will then leave the active site, and then the enzyme will revert back to its original shape, and then it can continue catalyzing this reaction over and over again. As long as it has substrate, then the enzyme will continue to convert the substrate to product. Okay, so that's our induced fit model. But this process is sometimes blocked. And there are two ways in which the process can be blocked. The first is through a pathway that we call competitive inhibition, where we have the substrate here. But in addition to the substrate, there's also a substrate mimic, which is an inhibitor. And in this example, the inhibitor has a similar shape to the substrate itself. And so instead of the substrate diffusing down and binding to the active site, the inhibitor can diffuse down and bind to the active site here. And block now the actual substrate from entering the enzyme. And so the enzyme gets stuck in this phase of the pathway because the inhibitor molecule can't actually be converted to a product. It just remains bound in the active site, and it blocks up the enzymatic pathway. So then we're left with a bunch of substrate that's never converted to product. Okay, so that's competitive inhibition, where the inhibitor is competing directly for binding site on the active site. In a competitive inhibition situation, if you add more substrate, sometimes you can outcompete the inhibitor for binding to the active site. So the amount of inhibition that happens is proportional to the amount of inhibitor that is present. If there's only a little bit of inhibitor, then there'll only be a little bit of inhibition because the substrate is much more plentiful. Okay, this is in contrast to this other type of inhibition called allosteric inhibition. In allosteric inhibition, we have, just like before, a substrate that is going to bind to our enzyme, but we have an inhibitor here, which is actually not the same shape as our substrate. And instead of binding to the enzyme at the active site, it binds at some off-site location, let's say down here on the enzyme. And what this causes is a change in shape of the enzyme. So the three-dimensional structure of the enzyme has changed shape, and now the substrate has no spot, it's changed the configuration of the active site so that the substrate can no longer bind. So if the substrate diffuses down here, it just bounces off, boop, and it can no longer convert its substrate to product. So allosteric inhibition, the amount of inhibition is going to be dependent on the amount of the inhibitor relative to the amount of the enzyme, not to the amount of substrate. So the amount of competitive inhibition that happens is the difference between the inhibitor and the relative amount of substrate. And in allosteric inhibition, the amount of inhibition happening is relative to the amount of inhibitor versus the amount of enzyme. Okay, so why do we care about these two types of inhibition? Where do we see this taking place? Well, a lot of drugs, both drugs that we would use like over the counter or prescribed by a doctor or illicit, are acting through one of these two pathways to change our enzymatic state. A perfect example of this is caffeine. Caffeine serves as an example of competitive inhibition where the inhibitor, the caffeine is the inhibitor, and it's binding to it's outcompeting its substrate, which is, or the actual substrate of the enzyme in your brain for binding. And this substrate that it's outcompeting is called adenosine. So adenosine is a molecule that when it builds up gives you the sense of fatigue. It binds to a receptor in your brain and gives you signals that you're tired. The way to kind of decrease your levels of adenosine is to go to sleep. That causes sleep is when adenosine is cleared out of your brain. But caffeine is a drug that mimics adenosine and will come in and bind to this fatigue receptor and prevent you from feeling fatigue. So drugs are often inhibiting enzymes that they inhibit, and that's why we use them. The other important part of these inhibition pathways is for maintaining homeostasis. So let me explain what I mean by that. Imagine you have an enzymatic pathway where you have enzyme A and then enzyme B and enzyme C, all working together to create a product. So coming into enzyme A is, let's say, a red substrate, and then A converts that red substrate to a purple substrate. And then B converts that purple substrate to a blue substrate, and enzyme C converts that blue substrate to a yellow substrate. So our end product of this whole chain of enzymes A, B, and C, is a yellow product. Well, imagine we only want so much of this yellow product. We don't want the levels of the yellow product to increase and increase and increase and increase. So the system is actually designed that when the levels of yellow product build up, so when levels of this levels of the yellow product increase as red is converted to purple and blue and yellow, and then the yellow product actually is an inhibitor of enzyme A. So that prevents A from converting the first step in our enzymatic pathway. A can no longer convert our red substrate into our purple substrate. So this is a really good way to balance levels of your product. Levels of yellow will increase until they reach a point where they are stopping a significant amount of the enzyme A from starting this initiation pathway. And then we will stop producing the yellow product. Maybe over time, the yellow product will be degraded in our body, and so levels of the yellow product will decrease, and that will relieve the inhibition on A, and then A will once again convert red to purple to blue, which will then build up the levels of yellow again, and then once again, yellow will inhibit A and will stop the process. So this is a way that we can control the amount of product made in our body. And this idea is called end product inhibition. So end product inhibition is when the end product of an enzymatic pathway inhibits the pathway from initiating, and in so controls the overall amount of end product produced. Okay, that is all. See you in class next week.